In this chapter, we're going to be introducing logic and proofs. In this lesson, we're going to look specifically at inductive and deductive reasoning.
All right, hi everybody. So in this particular chapter here, we're going to start to introduce some ideas in logic, and our goal is to kind of move you towards an understanding of proofs. We're not really going to explore this probably in the way that it really deserves. This is just an introduction to it, more than anything else here. So we're going to kind of lay a little bit of a foundation. We're probably going to be a little sloppy in some areas. I'm going to just admit that right to you right now. It's just because some of the expectations in the curriculum aren't they don't go very far. Okay, so we're not going to explore this in the kind of depth that you would, for example, at a university or whatever there. So we're going to introduce, first of all, two different types of reasoning. We're going to talk about inductive reasoning and deductive reasoning. Okay, both of which are important in the process of coming up with a proof here. So first of all, we're going to take a look at inductive reasoning. Okay, and inductive reasoning generalizes from specific examples. Okay, so it's based on observed patterns. Like it says here, inductive reasoning doesn't guarantee the conclusion is true, which is why we call the conclusion a conjecture. We're going to talk about that in a little bit more detail in just a little bit here. But basically, think of it like this. It's like you might get up one day and you go to the window and you look out and you see a white car go by. A couple minutes later, you see another white car go by. You see another white car go by immediately after, and you conclude, hey, all cars must be white because of the pattern that I'm seeing here. I am generalizing. I'm assuming that the pattern that I'm seeing continues. Okay, well, we know that that's not true, that not all cars are white there. But that's the problem with the inductive reasoning in a sense there, is that you don't know that pattern actually holds, because it might not be true that based on just a few examples that it's true for everything. Okay, but that's okay. There is actually a form of induction that you will see in mathematics that can be used to guarantee the truth of the conclusion, but that's not the sort of thing that we're looking at right now. What I want you to understand about inductive reasoning is that inductive reasoning is basically it leads to the question of the proof. Okay, if I can write it like that, I don't even know if maybe I'm not saying that very well here, but what I mean by that is, like in the process of trying to prove something, first of all, there's got to be like an idea. There's got to be some sort of pattern that you notice, and then you become interested. Well, does this continue? Does this carry on, right? So I see a bit of a pattern forming, and I'm going to make a conjecture. I'm going to assume that it keeps going, but then I got to use a different form of reasoning to determine whether or not that's a true conclusion. Now, just to illustrate, whoops, sorry, I forgot about that. Just to illustrate how this works here, let's take a quick look at something. Let's look at Pascal's triangle. Continue the rows based on what you believe the pattern should be here. Now, just give me a second here. After kind of reflecting on this, I think this would make a lot more sense if we kind of did this for the time being. I'm going to cross out that bottom row right there just for the moment here. And let's say that this is what I gave you. I said, continue the rows based on what you believe the pattern is. Okay, so I see a 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Okay, you might think that from that point here, that the pattern, you might assume that, well, the next row is probably 1, 4, 4, 4, 1, and then 1, 5, 5, 5, 5, 1. I mean, isn't that what I'm seeing there? Okay, and hey, you know what? That's a reasonable conclusion, kind of based on the pattern that I'm seeing there. Now, if I erase this, though, and show you the next row, okay, well, maybe that's not the pattern that I seem to be seeing here, because I was expecting 3 fours, and that's not what I'm seeing in the next row here. It must be a slightly different example. So now I'm going to change my conjecture based on this new one. And what you might notice here is that, okay, I've got that 4 there. It's that 6 that really jumps out at me, but notice that the 6 is placed between the 2 3s. And then I notice that the 4 is placed here between the 1 and the 3, between the 1 and the 3. And then it might occur to you, oh, I think I see what's going on here. what they're doing is they're adding the two numbers and giving me the number in between here. So I still got the ones out at the end here because that seems to be continuing. And then 1 and 4 is 5, 4 and 6 is 10, 6 and 4 is 10, 4 and 1 is 5. And that would be the next line. And then I might go one step further and go 1 and 5 is 6, 15, 20, 15, 6, and 1. And that is actually the pattern that we call Pascal's triangle. Okay, but without that, what is that? 1, 2, 3, 4. Without that fifth row, you might come up with a different pattern. So a conjecture is a conclusion based on previous examples. Okay, just like we were saying before, you see some examples. We're going to assume that the pattern continues. And that's basically our conjecture. And it may, or forgot to switch back. It may or may not be true. Okay, it may be that that pattern that you've established is correct. It may not. It's hard to say. Then the question becomes, well, how many examples do I have to see? You know, like what? How do I demonstrate this? Okay, because the issue is you support a conjecture with examples. The more examples you see. Okay, like the more examples you have, the more examples you have, the more we trust the conjecture. Even without a good proof, even without being, absolutely sure that of the mechanism as to why a conjecture might be true or not here, the more examples we have, the more likely we are to trust it. Okay. But the problem is you cannot prove a conjecture is true with examples unless, and this is a big unless you can provide an exhaustive supply, an exhaustive supply of examples. In other words, if I can show you, for example, let's go back to my car illustration. If you look out the window here and you say white car, white car, white car, can you prove that all cars are white using examples? Well, sure, if you could get every car that has existed or exists and show that they're all white. Okay, if you can provide that exhaustive set of examples. The thing is, that is in most cases, that's just not practical to do that. So although it can be challenging to prove a conjecture is true, all that you need to show is that conjecture is false is to provide a single counterexample. So if you think about what I've just established for you right here, all I'd have to show you, all I would need is one car. Not care. Wow, I'm having a day here. One car that isn't white. That would be my counterexample. Okay, all I would need to see is one car that isn't white, and I would know that that generalization I made of that pattern was incorrect. Okay, so I hope that gives you a little bit of a sense as to how inductive reasoning works. Let's take a look at some examples now. So here we go. In our example here, what we're going to do is we're going to establish a pattern. So note that if a is equal to 2, then a squared is 4, and a is less than a squared. 2 is less than 4. And if b is equal to 3, then b squared is equal to 9. And notice again that b is less than b squared. So from that, we could conclude, okay, that n is less than n squared for all values of n. And you might feel somewhat justified because you've got a couple of examples to show that. However, notice that if n is equal to a half, okay, that n squared is going to equal 1/4. And in that particular case here, 1/2 is actually larger than 1/4. So that's a place where my conjecture here breaks down. Now, And that happens an awful lot, right? So what we would then do here is we might go back and look at our conjecture and say, okay, I mean, I know that there's some examples that follow this, but maybe I just need to tweak the conjecture a little bit. And so one of the things that you might say here is, so I'm looking at these values of n. I might say as long as n is, let's say, greater than 1, then n is less than n squared for all values of n. Okay? And that's probably going to hold there, and that'll be fine. Let's take a look at another example there. Okay, so here's a conjecture that I'm going to give. If a is greater than b, then a squared is greater than b squared. And I got some examples. I know that if 5 is bigger than 3, 25 is bigger than 9, 7 is bigger than 6, 49 is bigger than 36. So give 2 more examples. Sure, we could give a bunch more examples here. I know that, for example, 1/2 is bigger than 1/3. Now, the reason I go to fractions here is because we just looked at a question where fractions were the issue here. But in this particular case here, if I square both sides, I get 1/4, and 1/4 is bigger than 1/9. Okay, so hey, that still works here. I know that 10 is bigger than 1, and when I square both sides here, 100 is bigger than 1. Didn't change anything here. But let's take a quick look at a counterexample here. What if a is -2, and I know that -2 is larger than -3, but -2 squared is actually less than -3 squared, because we get 4, and 4 is less than 9. Okay, so it breaks down there. So then we look back and say, okay, but we know that we've got a bunch of examples here. Is there maybe some way that we could tweak the conjecture? And yeah, we can do that here, as long as, for example, you've got something like this where 0 is the low one, and we're going to let b and a both be greater than 0 there. We're going to deal with positive numbers. We're still going to let a be greater than b, though, just to be consistent with the initial conjecture up here. Let's take a look at another one here. The sum of 1 and the square of an even number results in a prime number. So 2 squared plus 1 is 5. Okay, that's prime. 4 squared plus 1 is 17. There we go. So we're going to give 2 more examples here. Okay, well, let's take a quick look here. And I mean, it doesn't take long to find a couple more examples. I know that 10 squared plus 1 is 101. Okay, that works. 101 is a prime number. I know that, hey, 6 squared plus 1 is 37. And 37 is a prime number. So again, we start to feel pretty good about that conjecture because we've got some support for it. But, okay, give a counterexample. Well, okay, 8 squared plus 1 is 65, and 65 is not prime. Okay, 65 is odd, but it's not prime. It's divisible by 5. Okay, so how could we alter the conjecture here to make it work here? Well, this is going to be a little bit tough. Okay, and you know what? Maybe you can't come up with a nice tweak to that conjecture that kind of preserves the essence of the conjecture, but just allows it to work here. I mean, I've looked at this a bunch of different ways, and there's really this whole idea of finding that prime number. That is tough. And when you look at kind of the patterns in the even numbers, when you square them, that gets you and add 1 and gets you the primes there, it's hard to see a nice clean pattern in that. So how could the conjecture be altered? I don't know. Not in a way, certainly, I think that preserves that prime number here. Now look at the next question. It says, the sum of 1 and the square of an even number results in an odd number. Okay, so we're completely backing off the whole prime thing here. So can you give a counterexample to that? Oh, yikes. Well, no, I can't. I mean, I could think about that for a long time. Every time you square an even number, you will get an even number as a result. And if you add 1 to that, it automatically makes that an odd. Now, what I just said probably does prove this. But does your inability to come up with a counterexample prove it? And the answer is no. Just because you can't think of a counterexample doesn't mean that there isn't one. Okay? We don't know. So what we're looking here is to make that proof work, we actually need to have a different approach than what we've got going right now. Now, let's take a moment here. And actually, I tell you what, this is another question here. I think what I want to tweak here. I don't think that bottom row should have been there. I think that was a mistake here. So let's ignore that for right now. We're going to make a conjecture about the number of triangles with n rows. We're going to test the conjecture here. Okay, so here I've got one row and I've got one triangle. Here I've got the 2 rows and I've got 1, 2, 3, 4 triangles. With 3 rows, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got 9 triangles. And so what I might say here is if we have n rows, there are n squared triangles. Now, let's see if that works. So previously, actually, we did do that 4th row here. So let's keep going here. So I know that there was 9 there. So 9, 10, 11, 12, 13, 14, 15, 16. Okay, so when n was equal to 4, I had 16 triangles. Awesome. Let's keep going here. Let's build another row, see what happens. So down, down. I think I did that right. So 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. There we go. It seems to follow our conjecture. 25 triangles. That's wonderful. Okay. Does that prove it? No. But it certainly makes me comfortable or confident that we have seen a pattern there, right? Because I can keep going with that. Let's take a look at another one. When 2 points on the circumference of a circle are connected by a chord, it divides the area of the circle into 2 regions. Put 3 points on the circumference and of the next circle and connect them. So let's do that. That's right. We'll put a point there, there, and there, and then we're going to connect them. Okay, and we're going to see how many little regions we get here. We get 1, 2, 3, 4. So here, when I've got, let's say, 2 points, I've got 2 regions. Okay, here I've got 3 points, I've got 4 regions. Okay, well, this is looking like powers of 2. Let's do it again here. 1, 2, 3, 4. We're going to connect these in as many ways as possible here. So 1 across, and then actually we're going to go across here with our diagonals here. Now I am assuming, now that I've got 4 points here, I'm assuming I've got 8 regions here. So 1, 2, 3, 4, 5, 6, 7, 8. There we go. So I'm feeling really good about this pattern. So what we might say here, okay, and we'll do a couple more. I've got, 1, 2, 3, 4, 5 points here. I am guessing with 5 points, let's take a quick look here. So when n was equal to 2, I had 2. N is equal to 3, I had 4. So it's almost like the pattern. I'm going to guess right now, my conjecture is that with n points, there are 2 to the n minus 1 regions. Okay, so I'm going to connect this. We can do this. Make sure I got them all. There we go. So I'm assuming right now that this is going to be 16 different regions here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is looking fantastic. And one more. We've got the circle here, so we'll do one more here. Okay, but everything is looking good. Okay, I've made a conjecture. I've got some examples. Everything is following, so draw this all out. Now, one of the issues here is just making sure that you get all of them. I want to make sure that I've connected everything. Oh, I didn't connect those guys. Oops, straight across there. It's not perfect, but you get the idea. Okay, have I got everything connected? Is everybody connected to everyone? There should be 5 out of each one there. Okay, here we go. So 1, 2, 3, 4. Oh, sorry, by the way, I am predicting 32 here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Little one there. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. 31. Yeah, this is an interesting one because that pattern does seem to work. That pattern with powers of 2 does seem to work for a little while here, but then it breaks apart later on here. And this is the problem. This is why we talk about questions like this in the context of inductive reasoning, because we know that sometimes the pattern that we're seeing and that we assume continues isn't the one that's actually being followed. There is a pattern that is developing here, but it's a bit more complicated than just powers of 2 and being one less than powers of, being related to powers of 2. I'll just say it like that. There's a bit of a polynomial sort of relationship here. Anyway, that's a great example for illustrating some of the issues that pop up with inductive reasoning. Now, the other type of reasoning that we'd mentioned before, okay, is deductive reasoning. Okay, and deductive reasoning is a much different form of reasoning here. It's a type of reasoning that moves people from statements that are accepted as true to necessary conclusions. I like that word necessary, okay? So this is, and it's because of that word necessary here, this is the type of reasoning that we can use to prove that a conjecture, to prove that an idea is actually true. Okay, so now this is going to be a type of reason that we are going to explore in a lot more detail in other lessons here. We're not going to do much more with inductive reasoning at this point here, and we're not going to do much with deductive reasoning other than to kind of just establish sort of what it is and to talk about some of the definitions here. But then we're going to move on and look at this more in more detail in another lesson here. So first of all, take a look at this example right here. It says, what can be deduced from the following, assuming that the statements are true? And that is kind of what we're stuck with. We're going to assume that these two statements are true. So every whole number is an integer. 7 is a whole number. Okay, so let's just think about that. If those two statements are true, well, what does that mean? Well, that means that I can conclude, therefore, and I'll put the little symbol here for therefore, the 3 dots. Therefore, 7 is an integer. Okay, if all whole numbers are integers and 7 is a whole number, then 7 must be an integer. Water freezes at 0 degrees Celsius. The temperature outside is negative 10 degrees Celsius. Okay, now you could kind of fiddle with this situation a little bit, but I don't want you to. I don't want you to try to think around the problem. For right now, just kind of accept it the way it is here. So what this means is I could conclude, therefore, any water outside is frozen. Now, is that 100% true? Is it possible that there could be a scenario where there's water outside that isn't frozen? Yes. Yes, it could be. For example, at negative 10 degrees, there could be salt in the water that's keeping it from freezing. There could be, antifreeze. There could be other situations there. But just those two statements taken as they are, that's kind of what we want you to conclude here. Another classic one, and I know it's not here, but another classic one is you would see this in a bunch of texts or whatever. You might see something like this, where it would say, all men are mortal. And then you'll see Socrates is a man. And so what can we conclude? Well, we can conclude, therefore, Socrates is mortal. Okay. That one, I've seen that one in a bunch of different resources here. It's quite a common one here. Okay, so hopefully that gives you a little bit of an idea here. By accepting the truth of these premises here, we can make a conclusion, and based on the truth of those premises, we can guarantee the truth of the conclusion. So a theorem, and this is a little bit different than what we were looking at before here. A theorem is a statement which can be proved using logical or deductive reasoning, or it's the conclusion of a deductive argument. With induction, that conclusion is called a conjecture. Okay, so this one here is a theorem. So a mathematical statement or proposition, okay, because now we got to talk about this here. So is a statement that is either true or false. So this is going to become a bit of an issue here when we start talking about deductive reasoning, because deductive reasoning is based on statements that we're accepting as true, these propositions. So if that's the case, then we need to be able to decide whether or not a statement is true. In other words, we need to understand whether or not that is a proposition, whether it's something that we can work with deductively. So let's just take a quick look here. Here are propositions. All cows are brown. Okay. Now, is that true? No, that's false. But because I can determine whether it's true or false, okay, that's a proposition. The Earth is further from the sun than Venus. That's true. There is life on Mars. Now, here's the interesting. Well, I don't know. And the whole point of this question is here, whether you stand on one side or the other, whatever. There is life on Mars. I don't know. But it is either true or false. I might not know whether that's true or false, but I know that it is either true or false. 2 times 2 is equal to 5. That is not true. That is false. But, okay, that's still a proposition. Okay? Now, look at these next set here. Do you want to go to the movies? Clean up your room. 2x is equal to 2 plus x. This sentence is false here. Now, a few issues here. These are not propositions, and so the explanation is given just below here. The first statement is a question. Okay, so this is, this is interrogative. Okay, that's not a statement that can be made true or false. It's a question. Clean up your room. That is also not a proposition. That is an imperative. Okay, that's a command. Again, it's not something that can be true or false here. Now, this next one here is a little bit interesting. It is a like it says here, it is a declarative sentence here. 2x equals 2 plus x. But if you don't specify what x is, it's neither true nor false. Okay, if I state that x is a given value here, well, if I say that x is 2, then it's a true statement. If I say x is 3, well, then it's a false statement. So the way it sits right now, it's neither. There's not enough information given there. Okay, but it could go one way or the other. And this last one, here's a fun one. This sentence is false. This one, if you try to make this true, if this sentence is true, then it's false. Okay, well, that doesn't make any sense. Well, what if it's false? If this sentence is false, then it must be true. Okay, so this is actually a paradox and not a proposition. It's neither true nor false.